But welcome to this training action on tools for assessing microbial safety of water reuse. It will essentially be a training on two specific tools, which I'll mention later. Yeah, again, we're a small group, but just some quick announcements before. So, of course, we're recording this training action. I will just mute Patrick because there's background noise. Yeah, perfect. Thank you. Yeah, so we're recording this this training action. So if you don't want to be on camera, then feel free not to add your cameras. But we are a small group, so if you'd like to have your cameras on, then please feel free to turn those on. If you are not speaking, then please keep yourself muted so it doesn't create any background noise for the ones who are speaking. You can also put questions in the chat functionality on Teams. And then lastly, I already circulated this in the chat. There's a evaluation form that we would like to get input from those who are participating. The input will be valuable for improvements in future trainings. So for the agenda, we turned it around a little bit. So we'll first have just quickly an overview of the training objectives. Then we'll go into the two specific tools, which will be presented by colleagues of mine at KWR. So first on the SuTRa tool, tool number 31, and then on the QMRA Plus tool, tool number 26. And then at the very end, we'll have some time for discussion. And before I forget, but I think most of you know me, my name is Ralph Lotzbach, and I also work with the KWR Water Research Institute. And I'll put the link for the survey towards the end of the training action as well. Just quickly for the training objectives. So the idea is to provide insights into two specific tools for assessing microbial safety risks in water reuse scenarios and applications, including drinking water agriculture. We're looking at the key features and functionality, the purpose of the tools, and where applicable, the application. So we'll focus, as I said previously, on the SuTRa for subsurface removal of microbial organisms, which will be presented by Martin van der Schaans from KWR, and that will then be followed by Patrick Smates on the QMRA Plus tool to assess microbial safety risks for water use in agriculture. With that, then I will invite Martin first to present, and I'll see if I can hand you a control, then you can move the slides yourself. Yes, perfect. I don't hear you, Martin. Yes.
You hear me now?
Yes. Thank you.
Okay, great. Thank you. So welcome, everybody. Yeah, I would like to tell you something about a tool that we developed about, well, it's about transport and removal of microorganisms in the subsurface. And I made it together with Stefan Ross, who is an old colleague, and Patrick Smates, who will be telling more about another tool later in this meeting, and a few people who also helped out on the programming. How do I do page down? Here we go. Yes, so well, this project was, it had to do a lot about water and agriculture, and so we focused on managed aquifer recharge application because they offer a lot of benefits, including storage of water. And however, sometimes this water that you want to store, it may be contaminated with pathogens, and one of the, for example, plant disease. And one of the advantages of having managed aquifer recharge, so having the water flow through the soil before you abstract it again, is that these pathogens, they may be removed during storage and transport. So you get a kind of purification of your water. And well, there is basically future challenges, of course. Technically, if you want to know, okay, how many of these pathogens are removed, and one is that, well, the existing models, they are often quite complex and they require a quite high level of expertise. And secondly, that these removal parameters, that they are hard to estimate because they depend on a lot of factors, and well, and often the data that you need is not available. Struggling a bit with there. Yeah, so the audience of this tool, it is mainly directly users. We see professionals involved in the design and evaluation of MAR schemes. This can be, I'm now talking mainly about agriculture because that was the purpose of the project. But of course, the tool is not limited only to agricultural MAR. It can also be, for example, for drinking water application, because then you also want to have a purification of your water by soil passage. And basically what the tool does is it is a kind of database. So it predicts the properties of the transport and removal properties of pathogens, and you can make simple calculations of how the concentration of pathogens evolves after storage in the subsurface. And it's based on simple analytical equations, and it helps to guide the user to get a very first rough estimate, kind of ballpoint figure of your removal parameters. And so, basically your input parameters, what we know is that the removal of microorganism, it depends on your transport properties. For example, how long and how far the water travels through the soil. It depends on your aquifer properties, for example, grain size, but also whether the water is oxic or anoxic, what organism you're dealing with, and concentration, of course. And output of the tool is the properties, the transport properties of the organism, and that's mainly the sticking coefficient and the inactivation. And so sticking coefficient, that's how good they attach to soil particles, and inactivation is their die-off, and output concentration. And everything is made in as a Python package. You can download it or you can install it directly in Python just by typing pip install SuTRa, and then you are good to go. The only thing is that you need to be able to work with Python, of course. Okay, so like I said, if you want to do a full calculation of transport processes of microorganisms in the subsurface, then you have a lot of different processes that you have to take into consideration. And there is, of course, advection, so the organism flowing with the groundwater, but the organism may get attached to the soil, or he may detach again, or there may be die-off or inactivation. The sorbed organisms may also die off, but for the purpose of the study, we thought, okay, we're going to make a simplification. So we are going to focus on the advection term, so the organism flowing with the water, and the inactivation, because in general we see that for the peak concentrations, which is what we're focusing on, that those two parameters are the most important one. And then the impressive equation, it becomes slightly more easy to handle. You see that your concentration, it is basically a exponential decrease based on your attachment coefficient and your inactivation. And then here are a few equations that are used to calculate these equations. And basically your input, what you require is an inactivation or a die-off rate. You need to know the attachment coefficient, which is basically tells you, okay, in case a particle collides to a soil grain, what is the chance that it will actually stick to it? So it's also called sticking efficiency. You need to know some organism properties, the diameter and the Hamaker constant, and some hydrogeological properties. So basically you need to know in total 7 parameters to be able to do a prediction. And the focus of course, the one that we focus on this tool is estimating the inactivation and the attachment. And so let's look now at, so there is a website, read the docs, where it's explained how you can install the tool and also how to do a calculation. So I'm just going to show you one example from, which is also on this website. And so basically the first step is that you need to open the package. And for people who are familiar with working with Python, this is well, quite standard code, I would say. And then the second step is that you need to like enter the parameters in order to retrieve the properties of the organism. And so in this case, we want to know something about the characteroforum for anoxic redox condition with an organism diameter of 1.8 micron and a starting concentration of 1 microgram per liter. And that's what we enter here. And then there is well, this is again a kind of Python step that you have to basically initiate your calculation. And so you have to initiate your microbial removal function. And then you have to make the calculation and print the results. And so in this case, you do a calculation where we've also assigned a pH. I didn't show all that, a porosity and a start concentration and the redox condition. And then it will calculate that in this case, the output concentration is 8 to the power minus 12. So you have a very large removal. There are a number of organisms are pre-programmed, but maybe you want to use something that is not in there. So here we've made another example calculation for a bacteriophage MS2, which is often used as an indicator organism, or often used in tracer studies. And instead of retrieving the properties of this organism, we can enter them. And so, for example, in this case, we enter the parameters that are prescribed by the way the Dutch government prescribed that you have to do microbial safety analysis of drinking water production sites. And so we use a sticking efficiency of 0.001, which is the convention for oxic locations. And then the next step, which is so now I'm going to show you an example of where we use this tool. And what we did is this is an example of a numerical model that we made of a groundwater well. So you see here at the top there is a recharge, there is water infiltrating, and on the left there is a groundwater well that is producing water. And what we did is, so the mod flow, which is also being the hydrological model, it basically calculates how the water flows. So you get a kind of streamline, and then based on these points, so these points, they come from the mod flow model, and then these points, they are fed to the Python package, and then the Python package, the SuTRa package, it will calculate the concentration of the organism inside the well based on the input concentration that you define as a user. And the nice thing, one of the reasons why we wanted to do this in Python is that a lot of the hydrological models that are used to calculate, do hydrological calculations for ASR system, that they're also based in ModFlow. So we thought this would be a good combination. And so here you see some example of the results, where you see the log removal, so the decrease of concentration. And you see that at the top, the concentration is quite high, close to the ground surface. And as you get to greater depth, the concentration becomes lower until it is no longer a problem for example, producing drinking water. Let's see. Yeah, so here is also, so one of the reasons why we thought, so we do a lot of these calculations for drinking water companies, but a couple of years ago, we were also wanting to do a project with, how do you say that, horticulture and the glass. And we wanted to make a large subsurface water storage, but with many farmers combining their fresh water, so that we could have a large subsurface storage, so that you have a large efficiency and little losses. But we found out that they didn't want to do this. And the main reason was that they were afraid that if their neighbors had a certain plant disease and that would get inside the infiltrated water, that they didn't know whether their own plants would get the same disease. And so we thought, oh, apparently this is not only a problem in drinking water, but also in other fields of ASR application. And how you can use this tool is to, how we foresee it is that it can be a step in a QMRA, which my colleague Patrick will talk about more later, where you say, okay, I'm going to I have a few other steps before that. I have a certain water source, and maybe there is some pre-purification. There is injection of fresh water with pathogens. And then what I do with SuTRa is I compute, okay, what happens during the storage? Is there what reduction of pathogens do I expect? And then again, the results, they can feed into the remaining step of a QMRA, where you eventually look at, okay, what is, you can even maybe look at the infection risk. So what are the ongoing or future steps? What we would like to do is to also include parameters of some more indicator species, like E. coli and somatic colifax, which are often used, and human pathogens, and also have the removal parameters. Right now they are based on literature values, but we want to base them on a larger database with many field and column experiments. And so that is on the content side. And another thing that is on our wish list is to have it also integrated with we are making a graphical user interface to calculate removal of organic micropollutants. It's called Aqua Priori, and we are thinking of also integrating this tool there, so that the same platform can be used for making removal calculations. I think that's it for my part.
Thank you, Martin, for that explanation on the SuTRa tool. We've dedicated time at the end for questions and discussions, so maybe if those come up, then we can take them then. So I'd like to invite then Patrick to present on the QMRA Plus tool. Patrick, do you want to transition the slides yourself, or do you want me to do that for you?
Well, let's try if I can do it. So.
Okay, then let me give you control. It says I cannot give you control, but it might be because you're on your phone, probably.
Yeah, I'm now simultaneously on my phone and my computer, because the computer refuses to show me live.
Okay,
but then I'll ask you to forward.
Yes.
So thank you for the introduction, Roel. Yeah, so Patrick Smit, I've been working at KWR for over 20 years now. I'm mostly working on microbial safety of water, drinking water, bathing water, etc., and how to use quantitative microbial risk assessment for that. And I just saw that the first slide said Peter Smit, but it's Patrick Smit actually. So the whole idea of microbial safety came around up in the 1990s, when we realized that absence of E. coli doesn't really protect the safety of the water. The Milwaukee outbreak of diarrhea was a well-known outbreak, which really shifted the idea. So within drinking water, microbial safety since then has been really focusing on doing quantitative risk assessment, which I'll tell about a bit more later. Now, in more recent years, there's more attention to water shortage and the need for water reuse to make sure that we have enough fresh water available. But of course, this reused water can only be feasible when the water is safe. So please go to the next slide. If we're talking about water reuse, there's a lot of aspects to consider. You know, how is it really sustainable in terms of using materials and energy, etc., and the waste streams that you generate? How do you fit it in with legislation and regulations? Because you know, a lot of those regulations are not really considering water reuse, wastewater reuse in many ways. Then the points I'll be talking about mostly here is the water treatment technologies. What do you need to produce safe water? How can you assess whether you are meeting that? With regards to the health and safety, and of course that's related also to how you use the water. And then what Martin was just presenting is more on matching availability and demand. For example, the project he was talking about, storing water in winter and abstracting it in summer, which is also not really in this presentation. But when you start on water reuse, these are certainly things that you have to consider in all projects. Next slide, please. So as I said, Quantitative Microbial Risk Assessment, or QMRA, was originally started in the drinking water scene, where traditionally water was only checked for the absence of indicator organisms, especially E. coli or enterococci. But we also realized that these organisms, for example, are very sensitive to chlorine. So if you have a little bit of chlorine in the water, the indicator organisms may already be gone, but the actual pathogenic microorganisms may survive, especially, for example, Cryptosporidium and Giardia. So in the Netherlands in 2002, there came new legislation saying that if you produce drinking water for surface water, you have to perform a risk assessment, a quantitative risk assessment, to demonstrate that the drinking water is actually safe. And the reason for that is that we know that these pathogens are present in our drinking water sources. If we're talking about surface water, they receive treated wastewater, which still contains pathogens, but also combined sewer overflows and runoff from land. So there's many pathogens in the surface water sources. There we can measure them, but then once you start treating the water, the concentrations go down, typically with various treatment steps that either physically remove the organisms or inactivate them in the form of disinfection. So the concentration quickly drops below the concentration, below the detection limit. On the other hand, we know that even very low concentrations of pathogens can still cause serious infections, even if they are below detection limits. So that's why we developed QMRA to calculate or to estimate at least the concentration of those pathogens in the water after all the treatment steps. And then when you combine that with how much water people are consuming, then you know the number of pathogens that they are likely to ingest per day or per year. And with knowledge about the infectivity of the pathogens that we call the dose-response relationship. So the more pathogens you ingest, the more likely you are to develop infection and illness. We can also estimate the risk of infection. So this, since 2002, the drinking water companies in the Netherlands have been working a lot on this, and also internationally you see various countries that have used QMRA to come up with either risk standards or standards for treatment or other methods of making this risk management more quantitative. Next slide. Now, over the recent years, there's a lot more interest in water reuse, and not only for drinking water, but also for other purposes like irrigation and horticulture, or bathing water, or washing your car. So that makes the whole process of doing a risk assessment a bit more difficult, because we are looking at a lot more possible sources of your water. And of course, that also means a lot of different levels of pathogens in there. Then you may have a treatment or may not have a treatment, but also when you apply the water, there may be additional effects on the quality. So either, if you're talking about irrigation, for example, the method of application of the water, of irrigating the plants, will have an effect on the amount of pathogens that will be present on the plants. You do a spray irrigation on lettuce, the pathogens will tend to be contained on the leaves and therefore provide a higher hazard than if you use drip irrigation. And of course, also if you use it for toilet flushing, your exposure will be far less than if you use it for drinking water or if you're spraying plants with a garden hose. Then if you think about who is being exposed, there's also various groups to consider. Of course, the consumers of the products or of the water itself, people working in the field that are exposed to the water, public exposure either through the drift of spray irrigation or because it's in a park and people will play in the grass the next day or even play in the water or use the fountains that are using reused water. And there's also a consideration for the environment, which is more directed towards chemicals, because if you're reusing wastewater with a lot of chemical contaminants, actually by using it for irrigation, you will again spread that into the environment in different ways and maybe even enhance the infiltration into the underground. Microbially, the environment is not such a big concern because most of the microbes are already present in higher or lower numbers in the environments. So, next slide, please. So, what we did in previous projects and what we build onto within the B-WaterSmart project is to make quantitative microbial risk assessment more accessible to a wider audience, because the water safety in reuse projects is a very big issue, but most people are not so aware on how microbial risks exist and can be managed and how that is impacted by different choices in, for example, design of systems. So we want to develop an easy-to-use web tool that is transparent on how it's using data and it's science-based. So we include the most recent knowledge. Should be user-friendly because typically it will not only be microbial experts or risk management experts using this, but many stakeholders in a project can use the tool to come together and have discussions on what a system should look like. And of course, a safer system will have higher costs and higher use of resources. So you have to make a careful balance between safety and other objectives. It's also a useful tool if you want to introduce people into QMRA as a starting, let's say, education tool or training tool for people that will then develop further into QMRA. And it was also built in like in a stepwise where you don't really need previous knowledge to use the tool. You don't need your own data to use the tool. But once you're familiar with the process and you get more insights, you are able to make it more exact by including your own data or adopting different values, etc., in the tool. And basically, the tool is mostly used for comparing different scenarios in the design phase of a project, so that you can make the right decisions. So then the next slide, please. So I briefly explained QMRA in drinking water before. Can you click again, Roel? So the most simple form of doing a QMRA is making a point estimate where You set, for example, the average concentration of pathogens in the source water as a concentration, and then estimate how well they are removed by different treatment steps, also as a set value. And typically, that effect of a treatment step we express as a log reduction, because we know that we need many factors of reduction of pathogens to meet safe waters. So a 90% removal means 10% of the pathogens go through a process. Therefore, the concentration is reduced tenfold. So we call that a 1 log reduction. So depending on which process you're talking about, it can be more or less effective. For example, 3 log reduction therefore means 99.9 log removal. As an example, or to give an indication, for drinking water for some pathogens in the Netherlands, we need 9 log reduction. So that's 99 point many nines. Now, we also know that concentrations and treatment efficiency are not stable. They vary in time due to different factors. And also, there's some uncertainty involved in the data that you have on the efficiency of these processes. Therefore, we do a stochastic risk assessment using Monte Carlo simulations, which combine the uncertainties at each step of your risk assessment. So that means that you describe not one concentration, but a distribution, a probability distribution of concentrations, and also a probability distribution of log reductions. A Monte Carlo simulation means that each time you take a random number from each of these distributions, do your calculations to calculate a risk. I repeat that process 10,000 times, so you get 10,000 calculations of risk, which gives you a distribution of the risk estimate. So that gives you a better basis for decision making, especially if you've had a lot of uncertainties in these process steps. So the QMRA Plus tool also includes that stochastic risk assessment with these distributions. So now I think the next slide is the opening slide for the opening page for the tool. It's a freely accessible tool on the internet. However, at the moment we're having some issues with servers and other software problems. Therefore, at the moment it's not available, but we hope to get it up and running within a month. So, well, you can enter your name. There's no real login needed, but that means that you can save your results are saved so that you can continue on the next when you want to continue with your risk assessment. You can just log in and you get your previous filled in information. So next slide. Well, you can do various risk assessments. So either you start by creating a new risk assessment, or if you've already made some risk assessments, you can modify them and load the data you entered. And of course, you give those a name and you can give them a short description. Next slide. Then the first step within the risk assessment is defining your water source. And because we wanted to set up the tool as in a way that is easy to use, so you don't need previous data, and not many people have real data for their water sources when it comes to real pathogen monitoring, because pathogens are quite expensive to monitor. We've created a drop-down list with common water sources, so groundwater, surface water, sewage, rainwater as a rooftop harvesting, or rainwater as a stormwater harvesting. Of course, the second one is less clean. And when you select your water source, and you can also give it the name so you know what you are referring to, the tool will give you basic numbers for the bacteria, viruses, and protozoa. And we selected these 3 groups of pathogenic organisms because they all pose different challenges. Bacteria are typically present in high numbers and can be zoonotic, so they can be transferred from animals to humans, whereas viruses are generally human-specific. Maybe they're in slightly lower numbers, but they are very small, so filtration processes will be very different. and also the pathogenity of the viruses and their resistance to disinfection may be quite different. And similarly for protozoa, which are like Cryptosporidium and Giardia as the best known ones, they are typically very persistent in the environment and also very persistent for disinfection processes, but may be more vulnerable to, for example, filtration because they are slightly larger. Now, of course, we only mention these 3 groups, but we use for each group a what we call an index pathogen. So within the bacteria, we chose a bacteria Campylobacter, which is generally one of the most challenging bacteria or pathogens in water applications, and provide data for that organism. So if you're able to control the risk for that organisms, we expect that you control the risk for all the organisms. So for bacteria, we select Campylobacter. For viruses, we use we include the data for enterovirus, except for the part of the dose-response relationship, because there's no data for the enteroviruses complete, but we use rotavirus, which is considered a good indicator for that. And for protozoa, we focus on Cryptosporidium, which is the most persistent one. So for each organisms, we looked into literature and really looking at high-level literature, which already compiled a lot of other literature to provide a range of concentrations that you can expect for a source. So when you select a source, you will see that for each of the organisms, basic values are provided, but you can also see that these ranges may be quite large, because here the selection is, I think, treated sewage. Yeah. And there you see that the concentration of bacteria can vary between 1 in 1,000 liters and 1,000 per liter. So that gives an indication of, well, if you're just saying, well, sewage, there's very many types of sewage around the globe. So to cover them all, we provide a big range, and we describe that range through a probability distribution. Now, if you click that rule, I think it should show up. Yes, what happens when you hover over the information button, you get more information on what are bacteria, which ones have we used. Just some basic information for people that are not familiar with microbiology. Similarly, all the information buttons give you some information, and the text on the page gives you some guidance on how to select your selections in this part of the tool. So next, this is an example of what I was just talking about. So in the guidelines for drinking water quality by WHO, there are tables like this, which give broad ranges for pathogens in various water sources based on literature. The next slide. Okay, so when we have selected the source water, then we have to come up with water treatment, considering that we expect that water needs to be treated. And for that, on the left side, we have a large collection of common water treatment processes, and you can compile a treatment processes compile a system by simply dragging and dropping the processes that you want to explore or that are in your existing system, and add them to the process scheme. Next slide. And then, similar to the pathogens in the source water, here you get log removal values for the efficiency of such a treatment step. For example, here bank filtration, so passive soil filtration, depending on how it's designed, it can provide you with 2 to 6 log reduction of bacteria by the treatment process. Again, these ranges are modeled as probability distributions, so that the uncertainty that you have here is also propagated into the risk estimate. Next. Again, these log reductions are based on generic data, for example, or compile data, let's say, for example, the WHO guidance for drinking water quality, which provide you basic tables with quite large ranges. Interestingly, we've been working with WHO over the past years to update these tables and also provide a bit tighter ranges or better supported ranges for these log reductions. So once those come out, we'll have to adapt some of the tables to make sure that they are up to date with the current knowledge. A small issue is that not all processes are described in the guidelines for drinking water quality, for example, wastewater treatment systems. Therefore, we used other generic sources for those data. And in some cases, you see that they don't really correspond. One may be a bit more objective than positive than the other, especially if you look at the same process, they may provide some different ranges, which also indicates that although this tool is very easy to use and very accessible, as long as you don't have actual data from your own system, the uncertainty for these processes is quite large. So the tool in that case should not be used to, let's say, see if you comply with legislation, but rather to explore the ranges that you can get and get a feeling on how this works. Next slide. I already discussed it briefly. There's various pathogenic microorganisms that we know are affected by treatment. However, a lot of the experiments or practical measurements are not done with the actual pathogen itself because it's dangerous and quite hard and expensive, but indicator organisms are used. So for bacteria, generally E. coli is used because a lot of data is collected on that sense. For viruses, bacteriophages are used, which are viruses that affect bacteria. And these are used in experiments, or preferably if you have an existing system, are monitored in practice to evaluate the treatment efficiency. So it's not really an indicator for the presence of the pathogens, but rather on how efficient is a treatment for a certain type of pathogen. And similarly, we see different organisms for other pathogens. Next slide. Then, of course, it depends on how you use the water. That will affect how the different, how much water people are being exposed to. Here we see an example of lettuce. So if you have a lettuce, it may hold some water. So you presume how much water, or we use data from literature, or how much water is actually staying on those crops, and also estimate on how often do people eat these crops to come up with a number of exposures per year, because typically we express the risk of infection per year, and also how much water is then ingested, so we can calculate how many pathogens are included. And of course, this depends on the water use that you choose. So on the left, there's a list of presets. As a user, you can also say, okay, I'm looking at a different applications, or I have different data, so I can adapt either the number of events per year or the amount of water being ingested. Next slide. So once you've entered these three parts, the source, the treatment, and the intended use, you get a summary of the data that you have entered, and also more background on where the data is coming from. So next slide. So you can open up these tables and they will give you an overview of the data that is being used, and also the source of this data, so the scientific reference. Next slide. Then you say calculate, and the computer does the tool makes the Monte Carlo simulation, and you get a summary of the results. And the infection risk is, or the risk is calculated as an annual risk. And there are two typical standards being used globally, and especially by WHO. One is the annual risk of infection, which should be then less than 1 in 10,000 persons per year could get an infection from drinking water, which is also the Dutch standard. Or the DALIs are used, which goes beyond infection and also calculates the risk of really developing a disease and having adverse health effects, and how that reduces the total quality of life, which is expressed as a disability adjusted life year, or DALI. And for that, generally a standard of 1 in a million, or 1 micro DALI is used. And as a summary, it just tells you, hey, this is which pathogens are complying or not complying to these two standards. Next. The information is also provided as a in a graph with box plots, because as I said, we calculate the range of the risk based on all the uncertainties and the variation. The red line indicates, in this case, the risk of infection of 1 in 10,000. And you can see that, for example, bacteria, it's very likely that they comply. There's a slight chance that it exceeds that 10 to the minus 4 risk. Whereas for protozoa, you're pretty certain that you're not meeting a health target that we previously described. Next slide. The same data is also provided in a table, then with the mean estimate, and also the 5th and 95th percentiles and the median, and also provides you with some intermediate data, such as the concentration that you expect in the produced water. Next slide. Now, if you do have data from your own source, you can update the information. You can replace the information, the standard values, by values that you deduct from your own system, and we included a little Excel sheet that helps you do that, so that you can adapt those either log reductions or the concentrations in the source. Next slide. Then I'm actually considering, this is an example of what you then see, and then the table turns yellow because you have adapted the numbers, so you cannot refer anymore to the original literature used, but you included your own data. Next slide. Oh yeah, this one shifted just from there. Okay. Yeah, next one. So how did we use the tool in the B-WaterSmart Living Lab in Flanders? The concept there was to use effluent from a wastewater treatment system to either supplement the water in the raw water basin, which normally takes in water from the River Iser, with effluent with or without pre-treatment, or treating the effluent to such a standard that you can either add it later on into the drinking water process, or even directly into the drinking water system. So of course you will need different levels of treatment for that. And the health target being used was the 1 in 10,000 infection risk, similar to the Netherlands. That's a good, nice reference, and also it provides you with slightly stricter standards for the acceptable concentration of pathogens in the water. We also had a different part of the project that came up with a treatment process needed to provide chemical safety of the system, to remove micropollutants, etc. So we said, okay, with that design, would that also be sufficient for microbiology? And we would also see that it is sufficient. And within the project, we compared many scenarios, up to 20 scenarios. And what I think I really mostly found in that application is that the tool is very effective to introduce the method of QMRA, and also to play around with the numbers to get a feeling on how important is it. Because one of the things that it takes some adapting is especially thinking in log units. factor 2 in microbiology is not so important, so we only think about factor 10s basically when you're talking about safety. And you can also play around and having, taking out one pre-treatment processes as if it fails and see if you could still meet the risk of infection. I think that was the last slide for me. Yes.
Yes, thank you
So
very much.
right on time.
Yeah, very punctual. Thank you very much, and sorry for the mistake with the name at the very beginning. We've adjusted it so the slides that'll be circulated should have the correct name, Patrick.
Right.
Well, with that, maybe I can also invite Martin to turn his camera back on as well. So we've now we wanted to dedicate the last half hour, if it's shorter, it's shorter, but to get questions also from those who participated. If you have specific questions on the 2 specific tools or more around the application, then I would invite you to either raise your hand or turn your camera on to ask the questions. But in the meantime, while most of you are perhaps gathering your thoughts, I will just stop sharing the screen so we can see each other better. I do have maybe a question for each of you, Martin and Patrick, maybe starting with Martin. So from my understanding, the SuTRa tool requires knowledge on Python, but are there plans to make it more accessible to people who perhaps don't have expertise or knowledge on Python? Because you mentioned, for example, in your one slide on future developments and so forth about this graphical user interface as part of some other platform. Is that, for example, a way to make it more accessible to those who don't have specific expertise on or knowledge on Python?
Yeah, that's exactly the idea. So what the tool does, it has a kind of like some typical hydrological profiles. So for example, we have a river basin production site and a groundwater production site, and you just need to add some figures like the flow rate and the hydraulic permeability. So we already have that for organic micropollutants. It's what's currently being tested. We plan to release it in September. And it might be nice if people are interested to also make this available for microorganism, because from a mathematical perspective, it's almost the same as micropollutants. So how difficult can it be? That's
yeah, perfect. Thank you. And then maybe to you, Patrick, the question which I had was, so in the QMRA Plus tool has predefined values and ranges, but will there be a possibility perhaps to adjust those values manually so it fits more to the local context of those who are perhaps using it, or is that not really relevant? Or is that something that might be looked at in the future so that if they do want to comply to certain legislation, they're able to use the tool and monitor that? I see Patrick went off screen.
Sorry, yeah, my phone just said it's too hot to work, so I don't have a camera anymore.
No worries.
So what we did within B-WaterSmart is actually make that available so that people can adjust values in the tool themselves. The challenge is that if you're just saying, okay, I've got a rapid send filter, it really depends on how the filter has been designed, how it is being operated, how effective that filter is. And so that gives you an uncertainty. And especially if you're talking about disinfection, of course, the dose and the mixing and the hydraulic conditions will all affect how effective that process is. So if you're in the design phase, it's often very hard to really differentiate between those. And as long as you don't have real specific information about your system, you don't have a real scientific basis to adapt those values. However, it does allow you to say, okay, well, if I'm going to design a certain treatment process, I'm going to make sure that my rapid send filter is very effective. I'm going to choose, a big send height, quite a fine grain, and I'm going to monitor the turbidity. And I assume in that way that I'll be at the higher end of the log reduction. So say it would be somewhere between 1 and 4 log reductions that you can achieve, then you could adapt it to say, okay, well, if I presume that I'm able to get a 3 log reduction, you can make that reduction and make it, in that sense, more a tight risk assessment. But once you've built the systems to substantiate that, you will need to prove that you are achieving that in reality, which can be challenging, and it will take some monitoring. So for the evaluation of different scenarios, and hey, if we really put time, more effort in really getting this process really efficient, the tool allows you to play with those scenarios. But as a regulator, I would not accept a risk assessment solely based on either the data that is currently in the tool, or a personal estimate without it being backed up by data for a specific system. So if you really want to comply with a QMRA, you would need to substantiate the validity of the data that you're using to adapt those values in the tool.
Yeah. Thank you, Patrick. I'm just looking to see if there are any questions from the audience, but I don't see any. Maybe targeting some of the people that I do see on the list that I do know. So, for example, Peter and Han from the Watergroep. Maybe a question to the two of you, if you don't mind, or one of you. Do you see, for example, with the QMRA Plus tool, do you see the relevance of such a tool in the work that you do with the Watergroep? Is it something that you would consider applying, or do you have similar processes already in place to check quality of water that that you're able to supply? I don't know if Peter or Han would like to respond to that, if they're still on the call. Yes, Peter.
Yes, we are certainly looking at the QMRA together with Patrick to use it in other projects. We are still struggling with a large uncertainty about the results, and if we have to do all the measurements and quality control, it can be quite expensive. So that's it would be good if there's a very good database with relevant data. But at this moment, we are struggling how we can use this kind of tool for real projects. So, Han, do you know? Do you want to add something about it?
Yes. Well, the point is, I think that it's also in for the moment. I don't know the use in the Netherlands very well, but I think I know the use more or less in the United States, and there it has been used as a tool to pinpoint, let's say, a model treatment system. And based on this model treatment system that was brought forward and checked, users are open, let's say, to do improvements, but if they want to do them or amendments on this system, then they have to show that they are equally well in the treatment. So in that sense, it is very valuable because, let's say they put a standard for reuse based on the QMRA. And if you want to advance or you want to amend on this standard, then you should be able to show it with the data and with measurements. I think that's a good way to make use of this tool, because if you need to collect every time you have a system, you need to collect all the data and all the measurements to be able to convince legislation that your system is doing well. It's very hard and it's very expensive, let's say. do that. So I don't know if it is feasible to do it for every system and for every amendment. So in that sense, I think the approach in the United States is a good one. And I don't know what the future will bring. at least for us, we are experimenting with the reuse of the water, even for drinking water options, and it's a good backbone to see what the treatment segments of the strain can do. And so in that sense, it's very good. And also to evaluate the multivariate principle to see if there are like several options and which option is best for what. But in any case, it also shows, I think, that the way you operate the system, the way you maintain the system is very crucial. And also the knowing that the follow-up once you have this system is important. Well, it's very good to have this knowledge and to make sure that you keep your system and your treatment system well closely monitored. And that's another important aspect. But you can design it as perfect as you want. If you skip the maintenance, then your QMRA it's not any of any value anymore unless you have a continuous monitoring of it. But that's too expensive, I think. Yeah.
Yes, thank you, Patrick. Go ahead.
Yes. No, I recognize the remarks by Hen and Peter. Also on the, I mean, especially on collecting the data for your specific system. The question on, so how is it done in the Netherlands? Well, the legislation actually requires you to do these quite expensive and extensive measurements. And still, even then, at some point, you have to rely on literature because, well, even indicator organisms at some point in the treatment disappear. So there's a lot of attention on how to validate the performance of your system in a cheaper way. Because even though in the US, they've used this to set up a treatment system, but that also basically means that they disregarded part of the literature. As I said, WHO is updating those tables in the guidelines. We work closely with the University of Boulder, University of Colorado in Boulder, and other universities, really collecting every experiment ever being done on these treatment systems and trying to interpret that. And unfortunately, that means you basically get a big cloud of data. On the one hand, because as Han highlighted, the way you operate the system has a big impact. And unfortunately, all that literature often lacks a lot of relevant information. For example, how was it operated, or even what was the design of the treatment system tested. So lumping all that information together and coming up with a good example of, or a good estimate for a system based on, for example, design and operational and monitoring data, as in like online monitoring, is very challenging for a lot of processes. That's, for example, where the tool of Martin comes in, where we're not just saying, okay, we've got an infiltration abstraction, but you use easier measurements to get a better estimate of the log reduction that you can achieve with the infiltration. UV disinfection is another process where it's relatively easy because the operation and the conditions are quite easily controlled and monitored. So, and there's quite a lot of literature which provides you then with a good estimate. That's also why the tool, for example, has two different levels of UV treatment, either 20 millijoule per square centimeter or 40 millijoule per square centimeter, because of course with a higher dose you get also a higher disinfection, at least to some point. But one of the bottom lines is that even with every experiment done in the world, it's still very hard to that's only basically showing that it's very uncertain to predict it just based on easy to measure points or easy to measure variables in real life. And part of our research that we're doing also in other fields is really is trying to develop methods which allow you to monitor actual performance in reality in a cheaper way, in an efficient way, and so you can do it more frequent and at a reasonable cost. And one of the issues also is that for drinking water, we've always, said, okay, E. coli is enough, or we have a simple risk assessment, even if we're using surface water, which is basically, in many cases, diluted wastewater. But when you're really turning it into a wastewater reuse, then fear kicks in. People become very aware, and suddenly they will demand even lower risk than for a normal system. And that's what you see, for example, in California with direct potable reuse legislation, where they are, considering ridiculous high levels of log reduction requirements. As I said, in the Netherlands, we see that we need about 9 log. There they're talking about 14 to 20 log reduction of various pathogens, which makes it wastewater reuse basically not feasible because of the cost and also the downsides for the environment and energy, etc.
Thank you, Patrick. Just before moving on, just a quick reminder for those who are still on the call, because I see some people have been dropping out, to please fill in the evaluation survey. Hopefully those who've left will still see the chat and will be prompted to fill it in. Maybe with the remaining 15 or so minutes, maybe I'd like to just invite Martin maybe to say what maybe are the key messages that you'd like the remaining participants to go home with in relation to the SuTRa tool. And then Patrick, if you want to also do the same, but maybe starting with Martin. And unmute yourself, Martin. Sorry.
Sorry,
Yes, thank
no,
you.
I can only very much agree with what Patrick says, that in the end you can have the nicest tools in the world, but yeah, these microorganisms, they're very hard to predict. Wicked, I think, is the word.
Yeah.
And so yeah, in the end, once you have a system operating, of course, it's much better to use actual monitoring data to safeguard the quality. This is just a tool, maybe in the beginning or when you want to make certain changes, but it certainly won't replace any measurement.
Yeah, perfect. Thank you. And Patrick, if you have any additional remarks or takeaways.
Well, with everything said, we are also working in other projects to keep extending these tools. We have a tool that provides all the information from literature, at least, and that we will update with the WHO research. And we are also rethinking on how to combine this also with guidance on operation or guidance on monitoring, and you can do various levels of monitoring to prove that will narrow down that risk estimate. So then we recognize the issues, but it's not an easy issue to solve. And I still think that the tool as we have it really is very useful for that first step for people that are not experts to quickly get introduced into the topic and start understanding why certain things are very relevant. And the story will continue, I think. So.
Great, thank you. If there are no questions from the remaining participants, then I think we can end early. Then we all have 10 more minutes to do other things. So with that, I'd like to thank both Martin and Patrick for their time to present on the 2 respective tools, and also to the people who participate, and also especially to the ones who managed to stay out till the very end. So thank you very much. And have a good rest of your day.
Okay.
Bye-bye.
Bye, everyone.
Thank you. Bye.